So a few months ago, I found this fruit machine being advertised on eBay. And you know how it is when you see something on eBay and you think, I've got to have that. Even though the description said it wasn't all working and the owner wasn't quite sure why, I thought I'd buy it anyway and I could do it up. It could be a project and I'll fix it and make it as good as new. That was, I think, 4 months ago. And it's sat in the corner of my kitchen ever since. Never quite got round to looking at it, and my wife is now getting quite annoyed that it's always there. So, what I've decided to do instead of fixing it up is to actually rip it apart and find what components I can inside and see if I can use them in any other interesting projects as well. So, I've already taken out, this is the main PCB and the game board. Not sure, I might be able to get some components off that. Probably not that one that's just fallen off though. It's also got a bunch of interesting, there's a key switch and sort of various other switches there. This is a a note mechanism rather, so for an optical reading notes. I've got the entire 4-reel assembly, which has got some pretty heavy duty stepper motors going on in there. And just a whole bunch of lights and other stuff as well. So I'm going to sort of try to look at each component in turn, see if I can make it work, and then see if I can use it in a project in some way. So the first component I thought I'd take a look at is this. This is the feature reel assembly. So this was housed at the top of the cabinet, and it's a disc that spins round, and it's got the numbers 1 to 12 printed on it. The particular fruit machine I'm using was themed around snakes and ladders, so I'm guessing this is meant to represent the dice rolls that you can have on 2 dice. I'm not sure how you get the number 1 on rolling 2 dice, but never mind. Other than that, it's got 12 different positions here. And it's got 3 main components going into this assembly. So the first one, and the main one, is the stepper motor here in the centre. So the stepper motor is going to rotate around, and unlike a DC motor that just spins and round, a stepper motor is able to rotate in precise steps of fixed increments. And that's going to mean that we can control what number is displayed on the front of the wheel, like that. The next component is this little bit here, this sort of U-shaped black component here. This is a photosensor, and you'll notice also on the reel, on this arm of the reel here, there is a small black plastic tab. If I hold that a bit closer, so there. And what happens is, as the wheel rotates, there comes a point where that black tab goes between the arms of the photosensor, that U there. So at that point there, the way that this photosensor works is that there's a small beam of infrared light going between there normally. It's transmitted from one side and detected at the other. But at the point that the wheel is there, that black plastic tab gets in the way and the beam can no longer be detected. So this is going to be used to calibrate our wheel so that we know what position it's in, because if we rotate round to that position there, the beam is obstructed and we know which digit is facing forwards. And then the final component on this wheel is on this side here. We've got 3 bulbs, which are just regular light bulbs, and they're going to shine through and enable us to sort of see that nice bright arcade colour shining through the wheels there. Okay, so that's the 3 components. The next thing to do is to work out how to actually wire them to make them do something. And it became pretty obvious fairly quickly that looking at the colour of the cables was not going to help. When you actually look at the components itself, so the photosensor, I've got a blue, brown and pink cable coming off of. The bulbs are wired with white and grey, and the stepper motor has got basically a complete rainbow colour coming off it there. But this cable harness that's been plugged into it has got completely different colours on it. 2 greens, a handful of blacks, yellow, purple. So it was obvious that the colour of the connectors wasn't really going to mean anything. I'm going to have to work out some other way through a mixture of sort of experimentation and hopefully common sense to work out what needs to be wired where. So the bulbs is probably the easiest one to start with. Because they are not sensitive to which direction current passes through them. So all of the bulbs have one wire in common that is passed between them, and I'm going to treat that as a kind of a common ground that they all share. And they've all got one unique wire that just goes to that bulb as well. So we've got one ground wire and three anodes, which we're going to pass a positive current that way through the ground to choose which light to light up. So that accounts for 4 of the wires going out through the cable here. And I found out which ones they were by literally just tracing the wires and finding out where they're plugged in. The next thing to look at was the photosensor itself. Now, fortunately, this did have some markings on it. This is an Omron photosensor. So I looked up on the internet the product specification, and this has 3 wires going to it. There's positive 5 volt supply, there's a ground supply, and the third one is the sensor pin. And the sensor pin reads high when the photosensor is obstructed by the tab, and it reads low any other time. So I was able to plug those 3 wires in there, can account for them. That just leaves the motor itself. Now, stepper motors are quite clever things, but they come in lots of different varieties. You can get bipolar motors, unipolar motors, different sorts of winding, different numbers of leads coming off them as well. This did have a model number on it, actually. So it does have a model number there, you can see. But I looked that up and I couldn't really find out any useful product specification sheets. So I had to do it by experimentation instead. And to understand the experimentation, I probably need to explain a little bit more about how stepper motors work. So inside a stepper motor, you've got a number of coils of wire. And we'll take the example of a bipolar stepper motor to start with, because this is slightly more straightforward to understand, I think. So imagine here we've got 4 inputs to a stepper motor, 1, 2, 3, 4, and those are connected together in 2 coils. So 1 is connected to 2, 3 is connected to 4. If we were to pass a current from wire 1 to wire 2, that would generate a magnetic field that would either attract or repel the motor spindle. Likewise, if we were to do that between wires 3 and 4, we could then generate a magnetic field on a different axis to enable the motor to rotate. And by turning on and off those coils in a certain phase arrangement, we can make the motor spin round. Now, the way to do that is that sometimes you'll want a particular coil to attract the cogs of the motor spindle, and sometimes you'll want it to repel it. So in a bipolar motor, what you do is you actually reverse the direction of the current. Sometimes you'll want the current to go from 1 to 2 or from 3 to 4. And sometimes you'll want to reverse the current and have it flowing instead from 2 to 1 or 4 to 3. So it's kind of simpler to understand from the point of view of how it works. It's actually a little bit more complicated to control, because to reverse the direction of current through a section of the circuit, you'll need to use something like an H-bridge or something like that. Now let's look at the example of a unipolar stepper. So this example has now got 6 wires, and what we've done is we've kind of broken each of those 2 coils into 2. We've inserted a new wire in the middle. So now, instead of sending a current from 1 to 2, we can send it from 1 to 5 or from 2 to 5. So we've kind of split that single coil into 2. And now, to reverse the direction of the magnetic field on that side of the motor, we don't actually have to reverse the current through any section of the circuit. We just have to either activate the section of the circuit between 1 and 5 or between 2 and 5. 5 actually remains a common sort of sink or source on each side, so that can either be connected to ground or to 5 volts. And likewise, on the other phase at the bottom, we've got 3 and 4 with 6 in the middle. So we can either send a current from 6 to 3 or from 6 to 4, and that will reverse the direction of the magnetic field on that side. So this is the type of stepper motor which I've found on this real assembly. So how do I go about finding out which of those wires correspond to 1, 2, 3, 4, and 5, and 6. Well, we can kind of look at this diagram a bit more and actually figure out a little bit more. Supposing we pick an arbitrary set of wires and measure the resistance between them using a multimeter. So let's say we pick wire 1. The resistance between 1 and 5 is going to be a certain amount because it's got to go through a certain amount of wire at the top half of that side there. The resistance between 1 and 2 is going to be greater than that because we've got to go through all the coil of wire to get from 1 to 5, and then we also need to have the coil of wire between 5 and 2. The resistance between wire 1 and any of the wires down the bottom, well, they're not actually connected at all. So that's going to be an open circuit, and you'll measure, sort of an infinite resistance. So what we're looking for really to identify which wires are 1, 2, 3, and 4, what we can do is look for the pairs of wires that have the highest resistance between them but are connected. So with the theory out the way, what I did was I took my multimeter, set it to the resistance measurement setting, and then took the 2 probes and attached them to all of the pairs of wires of the 6 wires going to the stepper motor. So for every potential pairing, I measured the resistance between those 2 leads. And when I did that, I got the following table. So because I don't know at the moment which wire's which, I've just given them a letter, A, B, C, D, E, F. And I didn't want to give them the numbers because I didn't want to confuse that with the previous diagram. So these are just arbitrary letters assigned at the moment. And what we find is when I tested wire A against B, I got a reading of 1. Now, on a multimeter like this means that that is an open connection. They're not connected at all. When I connected wires A against C or A against D, I got the same reading against both, about 48 ohms. Now, what that says to me is that A must be the centre wire of a phase, and that C and D are going to either side of it. With E and F, I didn't get any connection at all, so that's an open circuit. If you then look at the middle line of the table and you see C connected to D, what you'll see there is a high resistance value, approximately double what the reading was from A to C or A to D. Or in fact, if you add together the resistance between A and C and A and D, you get the resistance between C and D. So that confirms what I suspected, is that on one of the phases, the coil has A in the middle and C and D either side. And then following the same process, if you look at B, that also must be a centre wire that has E and F either side of it. So that's identified the wires that's going to the stepper motor. I've identified the wires that were going to the photosensor from looking at the part number, and the light bulbs I just kind of took a bit of a guess from following the wiring. And with that in mind, I then set up the wiring as follows. So I have kept the same colouring convention as the wires that were used on the cable harness in my particular machine, but I wouldn't pay too much attention to that because I think that's just the colour of the cables they happen to have lying around when they made the harness. So what instead, I'll talk through what the wires actually are. So starting with the stepper motor at the top here. So these green wires here, these were wires A and B. Now remember, they were the common pins that went to the centre of each coil. And then I've got C, D, E and F. They are the wires that go to the end of each coil. And what I've done with those is I've plugged them in pairs. So C and D, they repair on one coil, and they are going to the first output of a motor driver. And I've got C and D, they are the wires at each end of the other coil, and they are going to the second output of the motor driver. So remember what I said about unipolar and bipolar motors. What I've effectively done here is I've taken a stepper that was a 6-wire unipolar stepper. I've ignored the 2 centre wires, that's these 2 green wires, and they're not going anywhere at all. And what I've done instead is I've taken the extreme edges of each coil and I've plugged them into this. This is an L298N chip, And this is going to act as an H bridge, which will reverse the direction of current between the outer two edges of each coil. So it's taken a unipolar motor and turned it into a bipolar motor, basically. That's what we're doing here. I'm powering this with 12 volt DC input, which I've got coming in here. And then I talked about phases of the stepper motor. So a phase is the pattern of turning on those coils or turning them particular positive or negative, or changing the direction of current to reverse the magnetic field. And so there's 4 phases that are controlled by these 4 inputs here, and they are going to pins 7 to 10 on my Arduino. So that's all the stepper motor connections. My cable harness had a ground wire in the middle here that just went nowhere, so I've left that in for completeness, but it didn't do anything. And the next thing I've got is the photosensor. So remember, that had 3 connections. It had a positive 5 volts, a ground, and a sensor pin. And that's coming down these wires here. So the ground wire here, this is connected to the ground rail at the bottom. We've got the 5 volts on the edge here, coming down the 5 volt line. And then the sensor pin I've got connected to digital pin 2 on my Arduino. And then finally, I've got the lamps. So these aren't actually being Arduino controlled at all. These are just constantly being lit. And in fact, I'm only lighting the center one of the 3. So I've got this common ground wire here that's connected to all of them. This black wire here, that's connected to ground. And then of these 3 purple wires, these control the anodes of the 3 lamps, and I've just plugged in the middle one. So that is my wiring. And now let's have a look at the code that's running on the Arduino. So to start with, so I said stepper motors come in different varieties, and one of the things that varies between them is how many steps it takes to complete an entire revolution. So for this particular stepper motor, each step corresponds to an angle of 7.5 degrees. Now that seems like a slightly crazy number, but that's actually a very common value. And what it means is that it takes 48 complete steps to turn the motor once all the way around. You can calculate this empirically by just increasing 1 step at a time and marking a point on the motor and seeing how long it takes to come back to where it starts. But I would start with this value to start with. It seems to be a very common value used across all sorts of stepper motors. And then we've got the numbers 1 to 12 written on the reel itself. So there's 12 different values that I potentially want to stop the reel at. And if there's 48 steps altogether, 12 values, it must take 4 steps to increase the reel by the whole next number. So that's just nice and easy. Now, you don't, strictly speaking, need to use an external library to control a stepper motor. All it does is writes high and low values to a series of pins in order. But I did use this Excel stepper library in this case. You can download this for free off the internet. It's a handy library because it includes some nice functions that accelerate and decelerate neatly and things like that. So it just takes care of a little bit of the programming, the low-level programming of the stepper motor if you want. So you can find that through an internet search pretty easily. I've plugged the sensor pin from the optical sensor into port 2 of my Arduino. And then in the global section, so this is the variables which are going to last throughout the life of the program, I create a stepper object using the Excel stepper library creation function. And I'm using these 4 pins. These are going to control the 4 phases of the stepper motor, 7, 8, 9, 10. And I'm also going to declare a target value, which is the number which I want to rotate the reel round until it's displayed at the front. Okay, so we're going to the setup function. So when the program first starts, I'm going to initiate a serial connection. I'm going to use that because I'm going to use the serial monitor as a way of inputting a value that I want the wheel to turn to. Obviously, you could do that lots of different ways. You could have a keypad, you could have any kind of input, button input or something, but just for testing purposes, I'm just going to type a number into the serial monitor and get the reel to go to that number. So I set up a serial connection, define the pin mode for the sensor, which is going to be an input obviously, and define a few default values for the speed and acceleration of the stepper motor. And then I call this calibrate reel function, which is the next function down. So remember what I said about the reel could be in any position when the code starts, and the motor has no kind of feedback mechanism itself to say where is the 0 position, but that's what we're going to use that photosensor for. So what the calibrate reel function does first of all is it sets the stepper to a fairly low speed, so 40 is relatively slow, and it then says to move the stepper by num steps. So remember, num steps was defined at the top of the code as the total number of steps required to do a complete revolution. So it's saying from wherever the stepper started, we're going to tell it to move 1 complete revolution round, and then so long as the sensor pin is not reading high, we're going to continue to run that process. So 1 step at a time, we're going to move a whole revolution around, and we're going to carry on doing that until the sensor pin reads high. When that does read high, obviously that while function will break, and we're going to stop the stepper, and we're going to call this set current position function to 0. So at the point we got to, when this reads high, we're going to then call that 0. And because we slowed down the stepper before we started running the calibration function, we'll then just set it back up to full speed again. So that's how we calibrate the motor. And then in the loop function, so like I said, we're going to send commands over the serial connection. So the first thing we'll do is check, has anything been sent? If it is, I'm going to be sending an integer value, so we'll pass whatever has been received on the serial connection as an int. It's possible that we want to recalibrate the reel while it's running without turning it off and on again. So I just put this in here. So I've said if you send the value 0, it's just going to call that calibrate reel function again. So it's always going to run it at least once when the program first starts, because it's defined in setup here. But we might also call it again by just sending the value 0. 0 is not a number on the wheel itself, so we know that if you send 0, you weren't trying to go to the number 0. Just put a little bit of debug information, and if we send any other integer other than a 0, we're going to call this stepper.moveTo function. Now this looks a little bit complicated. Remember, we defined steps per value at the top of the code as the number of steps the motor would have to turn to display the next digit. And that was equal to 4 because there were 48 steps and 12 numbers to display. So we're going to say whatever number we wanted to go to, we're going to multiply that by the number of steps it's going to take to get there. But, this is the only slightly complicated bit, the way that the numbers are written on the dial is in anti-clockwise order. And the way that the stepper library works is to go in clockwise order. So I'm just going to have to subtract whatever value we get from the total number of steps, and that will make it arrive at the right target number. And then this stepper.run function, this just says, it kind of is a bit like a polling function. It says to the stepper, okay, if any movement needs to happen in this frame, as in if we haven't got to this target value yet, move the correct step to get there. So that's the wiring all connected and the code uploaded to the Arduino. The question now is, does it work? Well, let's find out. So I'm going to reset the Arduino, and when I do that, the code will start from the beginning again. Remember, the first thing that should happen is that this reel will rotate until that optical sensor is obstructed, and then it's going to set that to the 0 position. So let's see if that happens. So I'm going to reset the Arduino here. Hopefully, there we go. Excellent. So it's rotated round, and if I show you at the bottom there, hopefully you can see the sensor there has been completely obstructed. So I've set this as the 0 position where 12 is at the top. Now if I tell it to go to another number, so I'm going to send a value through my serial connection of the number 5, for example, press enter, and the code rotates around to 5. Let's go to 9 instead. It goes forward to 9. Now let's try a harder value. So there's only 12 numbers on there, but I'm going to continue counting even beyond 12. So if I go to 13, it's a little bit like counting on a 24-hour clock. I actually get the number 1. If I go to, for example, 96, that should give me a total of 4 complete revolutions, and then we'll stop back on the 12 again, because that's obviously 4 times 12. Now let's go all the way back from 96 back to 1 again, and it should do 4 rotations in the other direction, ending up back at 1. There we go. So I'm pretty pleased with that. That's exactly as I expected. If it does become out of line for any reason, so if I was to, example, mess it up like that, so it's now saying the number 9 even though it thinks it's at 1. If that happens, what I can do is I can send the character 0 again, and that's going to repeat the initialization from the beginning, put it back to 12, and from then on it's going to work as expected again. So yeah, pretty pleased with that. So I hope you found that useful or interesting, or maybe both. In my next video, what I'm going to do is take another one of the components and see what I can make happen with it. So that I'm sort of building up this sort of Frankenstein's fruit machine out of all the different components wired together again. I'll put links in the description to the wiring diagram and the code that I'm using if you want to use it yourself in a similar puzzle. But if you've got any questions or comments, please let me know in the comments below. And if you'd like to see more projects like this, please check out my YouTube channel or my Patreon. Thanks very much for watching.